Look up at the skyline sliced apart by the colossal steel towers of the energy industry. Up there, horizontal axis wind turbines, or what the engineering world calls HAWTs, stand tall in the sky, carrying three massive blades slowly tearing through the air currents. To the vast majority, they are the ultimate symbol of the green energy era. But from a pragmatic mechanical perspective, they are bottomless money pits. Behind that macro facade lies an incredibly fragile and expensive design system. Millions of dollars are thrown into every single tower. A massive mechanical gearbox weighing tens of tons, paired with an intensely complex wind direction sensor system, is suspended hundreds of feet in the air, constantly enduring extreme torsional stress. When a tiny bearing wears out or an electronic circuit shorts, the entire system is forced to shut down. Super heavy cranes are mobilized at the cost of tens of thousands of dollars a day just to replace one broken component. That costly maintenance loop never ends. All of these massive operational costs, these expensive mechanical depreciations, are quietly dumped onto your monthly electricity bill. The suffocating feeling of being entirely dependent on a centralized power grid, bound by monopoly corporations setting energy prices, is a stifling reality. You cannot drag a 30-story wind tower into your backyard to escape that grip. But what if fluid mechanics didn't just have one single answer? From the dawn of engineering, humanity has possessed a completely asymmetrical principle for harvesting kinetic energy from the air. No skyscrapers needed, no sophisticated wind tracking sensors required, no gearboxes suspended in the sky. That core solution lies in a vertical axis and minimalist aerodynamic drag surfaces. A static system that receives mechanical pressure from all directions and brings the entire mechanical center of gravity down to the ground. This is the Vertical Axis Wind Turbine, or VAWT, a primitive structure operating on raw physical principles, where a simple mechanical drag differential is enough to convert a chaotic mass of air into static rotational kinetic energy. A machine born not to dominate the sky, but to seize back energy autonomy for the individual. To touch the roots of this principle, we must execute a spatial and temporal shift, leaving modern aerodynamic testing facilities behind to step into one of the harshest natural environments humanity has ever inhabited. Picture the arid plains of ancient Persia around the 7th to 9th centuries, AD. Imagine a space baked by a blazing sun, where howling desert winds carrying massive amounts of sand and dust sweep through settlements relentlessly for 120 days straight. The suffocating heat scorches the skin, and the severe drought forces life to shrink back. In a place where human endurance is stretched to its absolute limit by nature, the need for survival begins to speak. They needed to crush tough wheat grains to create food, but the muscular strength of humans and livestock was completely drained. It was exactly in the compression of that brutal space that ancient artisans were forced to find a way to subdue the invisible kinetic mass asserting its dominance out there. They did not craft delicate blades. They drove massive, vertical wooden shafts deep into the clay earth, stretching rough canvas and reeds across them. For the first time in mechanical history, a static structure was erected to directly endure the pressure of an air current. The winds slammed into the fabric screens. The mechanical drag forced the wooden shaft to spin, transferring kinetic energy directly down to massive grinding stones on the ground. Humans found the soothing, refreshing release from backbreaking physical labor not by avoiding nature, but by placing a moving mechanism right in the middle of its flow. Surviving the decay of time, that survival prototype slumbered until the modern era woke it up. In the early 20th century, the vertical axis principle was reborn in two classic forms. In 1922, Finnish engineer Sigurd Savonius reshaped the design by splitting a cylinder in half and offsetting the pieces. Nearly a decade later, in 1931, French inventor Georges Darrieus pushed the concept further by applying an airfoil cross-section, creating a curved structure resembling a giant egg beater. However, technological history is always full of pragmatic turns. When the oil crisis erupted in the 1970s, billions of dollars in global capital flooded into wind energy. In the race to scale up power output to a macro level, horizontal axis systems proved their mechanical scalability was far superior. Vertical axis turbines were quickly stripped of funding, pushed back into niche applications, and eventually left out in the cold by the global energy industry. But the laws of physics are never dictated by investment decisions. Brushing off the dust of history, let's pull this forgotten structure into a three-dimensional simulation space to dissect every force vector acting upon it. Through the lens of fluid dynamics, the vertical axis turbine is divided into two schools of physics, operating on completely opposing principles. The first school is the Savonius design, a machine driven purely by mechanical drag. Imagine a mass of air moving with high acceleration straight into the system. The Savonius rotor blades take the shape of two half cylinders. When the airflow slams into the concave surface of the first half cylinder, the entirety of the air's kinetic energy instantly converts into a direct pushing force. This concave surface takes the full physical pressure, compressing the airflow and pushing the blade forward. However, the spatial magic lies on the opposite side. At the exact same moment, the convex surface of the second half cylinder must push forward against the wind. Thanks to its smooth, curved structure, this convex surface parts the air layer to the sides seamlessly like a thin film of water, maintaining a drag coefficient significantly lower than the concave side. This exchange of force generates a massive pressure differential between the two sides of the central axis, mechanically forcing the entire system to rotate. Because of this direct drag principle, the Savonius system possesses immense starting torque. It packs a powerful physical pull, capable of initiating rotation even in the most stagnant wind speeds. But the price to pay is an agonizingly slow translational rotation. Its RPM is permanently locked and can never outpace the actual wind speed in the environment. This drags its kinetic to electrical conversion efficiency down to a sluggish 15%. The second school, the Darrieus model, is an aerodynamic magic trick driven by lift force. Instead of using blunt drag-catching shields, the Darrieus blades feature a teardrop cross-section, perfectly copying an airplane's airfoil profile. When an air current glides through this space, the asymmetrical shape of the surface splits the flow. The airflow traveling over the outer convex surface must cover a longer distance, forcing its velocity to spike. Applying Bernoulli's principle directly, this increase in flow velocity instantly triggers a drop in static pressure in that zone. The extreme pressure differential between the two surfaces generates a powerful lift force perpendicular to the wind flow. This lift continuously yanks the blade forward along its circular trajectory. Once it breaks free from its static state, the Darrieus system can slice through layers of air at extreme speeds. The tip speed ratio, or TSR, far exceeds the number 1, meaning the blade tears through space faster than the very wind blowing into it. This breakaway velocity pushes its power generation efficiency up to 35%. Its mechanical drawback is that its starting torque is practically zero, often requiring a starter motor to break the initial static inertia. Regardless of the school, the most superior spatial characteristic of a vertical axis turbine is its ability to absorb kinetic energy omnidirectionally. No matter which direction the chaotic airflow comes from, this structure continuously absorbs kinetic energy without needing a bulky wind tracking system. Moreover, the heaviest mass of the entire system, including the electromagnetic generator and gearbox, is planted firmly on the ground, making it easily accessible and minimizing physical labor during maintenance. However, the most honest weapon for positioning a technology is exposing its unbreakable physical limits. If you are dreaming of using a vertical axis turbine to supply grid power for a macro-scale farm, abandon it immediately. This system carries two fatal weaknesses. First is the spatial altitude trap. According to fluid dynamics equations, the potential energy of the wind is directly proportional to the cube of its velocity. This means that when wind speed doubles, the captured kinetic energy is amplified eightfold. Horizontal axis machines stretching hundreds of feet high are built exactly to access those stable, high-speed currents in the upper atmosphere. In contrast, placing a VAWT system near ground level means it must face a shredded aerodynamic environment. Friction from the terrain, obstruction from trees, and artificial concrete blocks constantly tear the airflow to pieces, causing wind speeds to plummet and creating countless turbulent vortices. By placing a machine in this spatial zone, you have already stripped away the majority of the input kinetic energy. Second, and also the most brutal mechanical Achilles heel, is material fatigue stress. A vertical axis blade is trapped in a cycle of physical torture. During a single rotation, it charges into the zone of maximum wind exposure, enduring terrifying bending forces, and then immediately sweeps back against the wind, where the applied force abruptly reverses. This alternating fluctuation of pushing and pulling stresses occurs multiple times per second. This relentless mechanical squeezing triggers metal fatigue. The crystal lattices inside the core structure begin to form millions of micro cracks, silently spreading until the entire structure is torn apart. The physical lifespan of a vertical axis blade is severely shortened. Finally, the Betz limit boundary affirms an absolute truth that no single turbine is capable of converting more than 59.3% of the wind's kinetic energy. While the most sophisticated horizontal axis technologies have approached the 50% mark, vertical axis machines pushed to their absolute limits still only achieve 30 to 40%. This design is strictly not for industrial investors, and absolutely not for those seeking maximum conversion efficiency. If vertical axis technology hits a physical wall, why haven't modern supermaterials saved it? Let's put on the hat of an investigative economic journalist and look straight at the naked truth of the macro system. The downfall of this technology is driven by a systemic barrier called path dependence. There is no sensational conspiracy theory here. Over the past 40 years, trillions of dollars from global finance have been poured into optimizing a single supply chain. The horizontal axis wind turbine, from manufacturing plants casting super heavy carbon fiber molds, to national technical safety testing standards, down to specialized spatial simulation software algorithms, everything has been absolutely standardized for HAWTs. Forcing a corporation to switch its assembly lines to produce vertical axis systems means tearing down this entire infrastructure legacy and rebuilding from scratch. Restructuring costs would push the price point to an illogical level. Furthermore, no banking institution will agree to disperse billions of dollars for a vertical axis project simply because it lacks a reliable historical operational database. The next fatal blow dealt to VAWTs is the law of economies of scale. Electrical energy only becomes cheap when turbines get increasingly massive. Current horizontal axis machines have easily leapfrogged from 1 megawatt to 15 megawatts per tower, but enlarging a vertical axis structure is a nightmare of physical stress. The entire static mass of a hundreds of tons giant rotor system will push straight down and crush the load-bearing bearing assembly at the base of the shaft. The mechanical friction generated at that scale cannot be resolved by current materials at a reasonable cost. Inability to scale up means an inability to lower the levelized cost of energy, or LCOE. Pushed out of the macro playground, the vertical axis system once clung to the small-scale segment for self-sufficient household power. But even on this front, it has been completely annihilated by solar power. Solar PV panels are an absolutely static mass of material. They absorb solar energy without any moving mechanical parts. They do not generate friction, they do not create metal fatigue, stress, they require no scheduled maintenance, and manufacturing costs have collapsed by 90% in just the past decade. Shelling out money for a silent matrix of solar panels offers a far sharper economic logic than gambling on a mechanical system vulnerable to constant physical fracturing. But the macroeconomic logic of mega corporations never represents the will of individuals craving autonomy. If you are someone who rejects dependency, questions imported technological black boxes, and wants to master the kinetic energy exchange process with your own hands, building a DIY Savonius wind turbine system is the safest and most pragmatic action path. It allows you to access the absolute fundamentals of mechanical laws. Here is the blueprint with a checklist of readily available industrial standard materials. First, the wind-catching blade structure. Do not look for expensive alloys. The optimal load-bearing material is a section of large PVC plastic pipe, 200 to 300 millimeters in diameter, or a metal drum sliced vertically in half. Second, the main drive shaft. You strictly must use an ultra-rigid threaded steel rod or a thick iron pipe to withstand continuous torsional forces. Third, the anchoring frame system. You need to weld a static rectangular steel frame, integrating two heavy-duty flange bearings, placed at the top and bottom to absolutely secure the shaft's rotational trajectory. Fourth, the heart of the machine, the generator. The core of success or failure lies right here. Absolutely do not use small toy motors. Their internal magnetic drag is far too high. Your rotor shaft will be deadlocked the moment the system connects to an electrical load. Hunt down salvaged electric bike motors, magnetic motors from hoverboards, or stepper motors pulled from industrial printers. They are extremely sensitive in generating voltage at low RPM ranges. Finally, the processing circuit cluster. You need a diode bridge rectifier to straighten out the chaotic AC alternating current from the motor into a flat DC direct current. Connect this circuit to a precise charge controller, with the final destination being a 12-volt storage battery. The execution process demands strict spatial precision. Slice the PVC pipe vertically into two perfectly symmetrical half cylinders. Secure these two wind-catching troughs onto two circular metal discs placed at both ends of the rotor. Here is the mechanical secret that dictates performance. Absolutely do not mount the two half cylinders touching tightly at the center of the axis. You must offset them, creating a static gap a few centimeters wide right in the middle. This aerodynamic gap is critically important. It allows a portion of the air mass being compressed on the concave side to escape straight through the back of the opposite blade, neutralizing excess air compression pressure, reducing friction, and smoothly accelerating the rotational velocity. Thread the steel rod straight through the center of the two circular discs and tighten with heavy-duty nuts. Drop the rotor assembly into the steel frame, locking both ends of the shaft through the flange bearings. At this exact step, a high-level physical failure risk is lurking. At all costs, the system must achieve absolute dynamic balance. If the two blades vary in weight, or the steel shaft is warped by even a few millimeters, disaster will strike. Under the mechanical pressure of a gust of wind, the eccentricity will generate massive multidirectional centrifugal force, creating resonant vibrations that will rip apart the steel bearings, snap the threaded shaft, and turn the PVC materials into violent projectiles carrying destructive kinetic energy. Precision in measurement is your only shield. When spun by hand, the rotor mass must glide smoothly, without any abnormal mechanical resistance. Once the space is stabilized, use a flexible coupling to align the threaded rod with the generator's central axis. Wire the electrical phases from the machine through the diode bridge rectifier system, push it into the charge controller, and send the current straight into the battery. When you watch the silent direct current voltage charging into your storage system, driven by the wind outside, you will grasp a profound philosophy. The fewer complex moving parts a machine has, the more its engineering nature reaches ultimate sophistication. Understanding and handcrafting a machine that transfers energy from the air doesn't just solve an off-grid electrical problem, it is a physical liberation. A perfectly calibrated vertical axis design boasts an exceptional physical lifespan, mechanical depreciation that is practically zero, and is ready to outlast the very structures sheltering it. It statically absorbs kinetic energy and never demands cruel hidden costs. Our entrapment by giant corporations stems from a refusal to master basic physical principles. Take these action blueprints off the screen, put your hands on the metal, and actualize the power of autonomy so that no monopolistic structure can ever bind your living space.